We left off talking about salinity and the effect salinity has at the surface as well as in at depth, and how that changes across latitudes. And this is going to be very important as we continue to talk about density. Even though salinity seems as the obvious difference among, say, seawater as opposed to freshwater, temperature actually has the greatest influence on the density of surface waters, and salinity to a lesser degree. These two factors together are going to what cause the major circulation. The deep ocean itself is actually more dense than surface waters. 5% doesn't sound like a lot, but it's actually quite a bit. And when we're talking about the surface waters and latitude, we can sort of compare and contrast low latitude water versus high latitude water in terms of, all of the factors. But if you look at figure 5.22 in the book, you'll see that, there's a lot to do with salinity as well. So we're going to continue to talk about that as we go on and talk about circulation. So low latitudes. Low latitudes are basically the equator all the way up to the tropics. At low latitudes, we have low density. And even though we were just talking about salinity, and we talked about how, especially around the tropics and a little bit lesser at the equator, it's a lot saltier there, you have to go back and remember the function of temperature here. At low latitudes, the temperature of the surface water is much higher, and the warmth of that water overpowers the slightly saltier nature. And the degree of which we're talking about temperature changes vastly. When we're talking about high latitudes, the surface water can be very cold, only a degree to maybe 5 on a good day above freezing. Whereas when we're talking about surface waters down at the equator, we're talking about 80 degrees Fahrenheit, just 20 plus. So it's a much bigger scale we're talking about than we're talking about salinity. You saw this when you made your temperature and salinity profiles, where temperature had a much wider scale and salinity was very truncated. So when we're talking about density, the driving factor is temperature. So low latitudes are low density because they're warmer. High latitudes are higher surface densities because they're colder. At the poles, this cold water, during certain times of the year and during certain climatic functions, they can also get salty for a period of time, but they don't stay salty for long because the salty water separates from the cold, fresher water and it sinks. And this starts, and this term is one you need to know, and that is density-driven circulation. This is exactly equal to thermohaline. I'm writing off the side, haline. I really need a pen. Thermohaline circulation and density-driven circulation are both driven by the differences in density at the top and the bottom of the ocean. So that's an important concept to understand. And thermo obviously means temperature, haline means salt, and the two of them together control density. I cannot overstate enough the importance of these three graphs, especially combined with the sort of Y graph we had for salinity. I know it's really easy to just draw these, or not, as some of you don't, but they're important to know and to understand. And when I say that you'll see them again, I hope you know what I mean. The graph on the upper left, this one, shows you depth versus just plain old density. So we have, again, depth, density. And then we have, at high latitudes, it's basically the same top to bottom. Density is lower when we're at low latitudes. Simple diagram. Temperature. You've seen this before because you kind of did this graph. We have increasing temperature, increasing depth. At the poles, it's cold all the way down. Other places, it starts out warm and then gets almost to the same temperature. Those are important to know if ever, for instance, you are given a graph with all of this stuff taken off it and just asked to identify on the shape what parameter it's measuring. Finally, at the bottom, we've put them together. So we have three so far. We have the density, we have temp, and if you think back, we had the salinity one that looks like this and like that, where this is increasing salinity up here. And at what latitude was it saltier? The lower latitudes, it was saltier. This would be the poles. And you should know this one, and this one. I'm going to make you practice them in class, but you should know those graphs. So take a little bit of time to like think about what they mean. We've talked about clines before. I know we've talked about thermocline, the layer of rapidly changing temperature. In the last video, we talked about halocline, which is the layer was rapidly changing salinity. One of the things that I hope you've recognized by now is that clines, when you look at profiles, look different than you would expect. In a typical cline, let's do a thermocline. So we have temp on the top. You would start out warm and get cold. And you would expect rapidly changing. A lot of you are drawn to the notion that this means this area, where there's a lot of change. It looks like in the graph, but that's not. The clines are the areas where the graph is almost horizontal. So those are clines. Pycnocline is a layer of rapidly changing density. Pycno is going to mean, oops, screen's frozen, hold on. I hope that worked. Sorry, my computer froze. So the pycnocline is more common in areas where you have a high differential between a layer of surface water that's less dense, an area of lower, deeper water that's more dense. Together, these three clines together, these ones are magic ones. Oh, here we go. These are the three clines you need to know, and they all typically occur at that depth. So we're talking about 300 to 1,000 meters, give or take. And again, as you know from the graphs you guys made, they are somewhere in between there. They may not occur across the whole area. Sometimes they're at 600 meters, sometimes they're at 200 meters. It's an approximation. These clines together are biologically wildly important. They provide a barrier, and I know that seems strange. You're like, water's water, what does it mean? But for very small organisms, in particular migrating organisms like diatoms and other small phytoplankton that migrate up and down the water column, that it is really basically impossible for them to move across those layers of clines. So you end up with an area of surface water that is not just, different in its physical parameters like chemistry, in terms of temperature, salinity, and density, but also in terms of its biological nature, because you can't really get them to go across the clines, those small organisms that can kind of define an ecosystem. This gives rise to sort of the layer cake idea of the ocean. And this is going to be a really important concept for the rest of this course. So pay attention, I guess. We have a mixed surface layer at the top. It's basically the top to 300 meters. Some books will say 200 meters. It's basically the idea. This tends to be the least density water. It's well mixed. It's affected by the waves, currents, tides. It interacts with the atmosphere. It frequently has the largest amount of dissolved gases in it. And it's what occurs above a strong permanent thermocline. Sometimes within the mixed layer, there will be a smaller seasonal thermocline, not always, but the strong permanent thermocline is kind of the bottom of the mixed surface layer. Right, so it goes, so far we have mixed, we're kind of making a 3-layer cake. And this is going to be horrifically bad drawing. So far we have the mixed surface layer. And then I'm just going to put TC for thermocline. Is the first layer of icing between the mixed surface layer and what's below it, which is what we will call upper water. There's some other, some books call it intermediate water. Technically, the clines are part of the upper water. So these two would kind of be together. Draw a little bracket. And then finally, we have deep ocean water, which is involved in deep currents. It's below 1,000 meters. It's deep. It's dark. It's not affected by light or biology. And if we were to draw it proportionally, because you know how deep the ocean is. Surface layer, the intermediate layer, and most of the ocean is deep. And it's pretty uneven layering system. We will talk more about the deep ocean water when we do currents and the masses, but you should know that those layers occur. The first question is what happens to divers as they descend in terms of temp. It depends on where you start, but since most diving happens in the tropics, we'll talk about there. Initially, you're in fairly warm water. Sometimes people don't understand why divers wear wetsuits because they swim and they're like, oh, it's so warm. Well, you should know from having some experience either diving or in a pool that the deeper you go in the water column, the colder it gets. So, they feel a change in temperature. For a while, the temperature is the same. Then they hit the cline. There's a rapid change in temperature. When they get below it, there's another layer of the same temperature. So if we're looking at a depth profile, we can now label most parts of it. We can make this, let me go back. We'll put it right on top. Do temp and depth. And let's say we have a low latitude curve where it starts at warm and gets cold. We've been labeling the cline before. We'll do it here. That's the thermocline. And in pink, we have the picnals. We've talked about picnals, isos before. Isothermal is the area where the temperature stays the same for across certain depths. Isopicnals are lines where the density stays the same. So you should be able to identify on a graph now 2 parts, not just the cline, but also the picnals if I give you a depth profile. We're going to stop there. It's a 12-minute video. That's not too bad. And we will do desalination as our last video.